Good morning, one and all. In today's lecture, we have to discuss the another concept of stability, that is a transient state stability and its phasor diagram. In the previous lecture, we had discussed the Park transformation of that stability. In that case, we have to just convert the three-phase system into the two-phase system for the analysis purpose and for the to make the system more stable and to analyze more precisely. The Park transformation are generally preferred. Okay, so in today's lecture, we have to discuss the transient state analysis. So what is that about the transient state analysis? The ability of the system to retain their synchronism following the disturbance sustaining for the reasonably for the long period. Means what? Whenever the system should be the unsynchronized because of the any disturbance for the reasonably for the long period, the ability to retain their synchronization means what? The system should retain their original position even there is the disturbance should be attained for the reasonably for the long duration as compared to the steady state. Then the transient that state is called as transient state analysis. Okay, the system that suffers from the sudden change or the large disturbance, the, the steady state stability limit is a maximum power that transfer without the system becoming the unstable. Means what? Whenever the system should retain their original position after the disturbance should be the occurred like the sudden change or the large disturbance for the reasonably for the long period as compared to the steady state, then that's called analysis is called steady transient state analysis. In that condition, that transient stability limit is nothing but what? The maximum power that transfer without the system becoming the unstable at a synchronization point. Means what? Whenever the transient stability should be the disturbed, it's the maximum power that transfer without the system becoming unstable. That power is called as transient stability power, and that limit is called as transient state limit of that concerned system. What are the different factor on which the transient stability should be the affected? Okay, number one, improved steady state stability. If you have to improve the steady state stability, automatically the transient state analysis, transient state stability should be improved. Whereas high speed fault clearing, if you have to improve the high speed fault clearing, means what? Fault clearing agar अपन ने that fault clearing, it should be the fasted as compared to the normal condition, then the transient state stability should be improved. Number third, speed recloser of that high speed recloser of that circuit breakers. Okay, single pole switching, if you have to use the multiple switching, multiple pole switching or the double pole switching, then what happens? There is a time lag between that the system should be the reclose that breaker, but the single pole switching में उसका जो भी time ऑपरेशन टाइम रहेगा वो कम रहेगा, सो दैट द ट्रांसिएंट स्टेट स्टेबिलिटी शुड बी इंप्रूव्ड. ओके, दैट large machine inertia, if you have to increase the machine inertia, automatically the transient stability should be improved. Whereas low transient reactance से भी transient stability improved होगी. high gain exciter, अगर excitation अपन ने बढ़ा दिया, it's again increase the transient stability and the braking resistance. Okay, if you have to just discuss observe this diagram, that is a waveform on which the fault current should be there. It should be it's nothing but the normal current is that, and the fault current that time is nothing but what? This is the time that the time for the sub transient is less, and for the transient it is nothing but a higher one, and for the steady state is nothing but the constant one. Okay, तो constant one to steady state stability में जो current था वो क्या था? It's nothing but a constant one. It does not disturb for the long period, whereas for the transient state it is nothing but that disturbance should be for the long period. That's we have to observe. That is nothing but this is we have to observe. That is nothing but that is a large disturbance of that fault current. That is nothing but कौन सा current है? That is a fault current. Okay, and if you have to just in that transient of the disturbance should not be the cleared, then the system is called as sub-transient system. Okay, that we have to sub-transient system we have to discuss in the later on. First we have to concentrate on that transient state stability and its phasor diagram. Okay, so this is nothing but a transient state analysis there, and now we have to discuss the phasor diagram related with the transient state analysis. Okay, that whenever we have to discuss the transient state phasor diagram, first we have to discuss about what is what is the different parameters that we have to consider while deriving the phasor diagram of that of the synchronous motor in the transient state. Okay, transient state में अगर अपने को फेजर डायग्राम निकालना है सिंक्रोनस मोटर का, तो फर्स्ट वी हैव टू डिस्कस द डिफरेंट पैरामीटर ऑफ द सिंक्रोनस मोटर इन द स्टेडी स्टेट. अगर स्टेडी स्टेट में कन्वर्ट किया, देन वी हैव टू then it's easy to understand the transient state phasor diagram. For that case, if the armature current is slow, very slow, then the field current should be is nothing but the constant compared with the transient decrement. Okay, the fictitious excitation voltage, that is nothing but the EQ, is generally proportional to the field current and also remain constant in terms of that field winding of that synchronous motor. If there is a quadrature axis rotor circuit, the current, that is nothing but the IQ, that is nothing but the it's equal to remains to the zero, and so does the nothing but the fictitious armature voltage is nothing but the ED. So that is fictitious excitation voltage कितना है, EQ है. Fictitious armature voltage कितना है, that is nothing but the ED है. What is current is nothing but the quadrature current is nothing but the IQ is also zero. The terminal voltage V is however it's different for the constant voltage, that is nothing but the E is equal to J EQ by changing the synchronous impedance drop. Okay, so the steady state voltage equation and the vector diagram are valid only for the slow changes, and the IF and the EQ are generally constant during such changes. Okay, so the fictitious internal armature voltage. So first we have to finding out for the parameters. Steady state में parameters कौन से रहने वाले हैं? सबसे पहले ED. Okay, and this is nothing but the total voltage behind the transient impedance or the transient internal voltage. अगर मैं जो transient अगर steady state internal voltage निकालना है तो मुझे क्या निकलेगा, E is equal to ED plus JEQ. Whereas for the fictitious internal armature voltage किसके साथ redefine कर रहा है, it's nothing but directly related with the field flux. Okay, so field flux के साथ directly proportional. So that's EQ dash is nothing but the omega MF upon LFF. LFF is nothing but the self inductance, and the MF is nothing but the mutual field inductance impedance, and is nothing but the that is nothing but the flux linkage, that is a psi into the F. Okay, directly proportional to the flux linkage. If it is shown that the quadrature axis terminal voltage VQ is generally differed from the EQ dash by the quadrature axis transient impedance drop, means what transient impedance drop is play the very important role while we are to changing the system from the steady state to the transient state. Okay, so that the difference between the EQ and the EQ dash, EQ क्या है steady state में, और EQ dash क्या है, it's a different quadrature axis terminal voltage in terms of the transient state. Okay, the friction is internal armature voltage, under the transient state, that is EQ dash is nothing but what, EQ minus XD ID is equal to EQ dash minus XD dash ID. So for the simplification, if there is a quadrature axis rotor circuit is there, the flux linkage is assumed to be that flux linkage क्या हो जाएगा, कांस्टेंट हो जाएगा. अगर फ्लक्स लिंकेज अगर कांस्टेंट हो गया तो डायरेक्टली क्या होने वाला है, एंड द ED dash is should be proportional to the linkage. Thus the totally that is nothing but the EQ dash था, और this is nothing but internal quadrature axis internal terminal voltage under the transient state, and this is nothing but the direct axis internal voltage under the transient state is omega mg LGG into the flux linkage of that quadrature axis rotor circuit. So this is nothing but the ED dash omega, that is a 1, and this is nothing but the 2. Okay, so ED dash is equal to omega mg LGG into the psi G. So the total voltage behind the transient impedance or the transient internal terminal voltage is given by E dash is equal to ED dash plus J EQ dash. ओके अगर मुझे सेम अगर मुझे सब ट्रांसिएंट में निकालना रहेगा तो मैं क्या करूंगा ई डी डबल डैश आएगा ई डबल डैश इज इक्वल टू ई डी डैश डबल डैश प्लस जे ई क्यू डबल डैश. Okay, so the direct axis and the quadrature axis are studied, but the E dash and the EQ dash are respectively that the voltage is a constant on the assumption of what that omega that is a psi g and the that is a flux linkage under the armature axis and under the field axis it should be the constant rate. If it is greater than the armature terminal voltage by the amount of the transient impedance drop, which consists of the resistance and the transient reactance component. If it is less, then the excitation voltage should be difference, and if it is greater, then the by the amount of the which is consists of the resistance and the transient reactance component. एक तो greater रहेगा और less रहेगा. अगर less than internal voltage by the difference of the synchronous impedance and the transient impedance drop. Synchronous impedance and the transient impedance drop, it play the very important role while defining the phasor diagram of that concerned transient state analysis of the synchronous motor. Okay, so under the steady state preceding the change of the armature current, the non voltage vector E should be the lies on the quadrature axis. That is ED is equal to 0. So thus the corresponding value of that ED dash and the EQ dash must be the computed by the adding the IQ XQ minus XQ dash to the 0 and by subtracting by the ED minus G from the EQ. So अगर मैं इसको simplify करूँगा, then so we are getting study, but the steady state with respect to the transient state दोनों का parameters अपने को निकालने पड़ेंगे, and just we are to subtracting equal to the 0 from the EQ. Thus, during the change of the armature current, E dash remains the constant. E should be varied from the quadrature axis unless the EQ should be equal to the XQ is equal to XQ dash. So suppose the component ID and the IQ is nothing but the armature current undergo the change of that and del of ID and the del of IQ respectively. That is nothing but the change of that current under the quadrature and the direct axis under the steady state and the transient state. The corresponding change in the other quantities are is nothing but to follow. Number one, that is nothing but the del of flux linkage is equal to 0. Del of flux linkage under the armature axis is equal to the 0. Under the direct axis is nothing but the minus LD dash del of ID and the minus LQ dash del of IQ. That's under the quadrature axis flux linkage. Next parameter as del of IF is equal to what? क्या है? Del of ID. अब what is the del of ID? Del of ID is nothing but the what? LD minus LD dash upon MF into the del of ID. Same for the del of IG that we are to getting. Then the del of EQ, that is the internal terminal voltage under the quadrature axis, XD minus XD dash del of ID minus इसमें del of ED क्या होगा? Minus of XQ minus XQ dash del of IQ. Now this is nothing but the change क्या है? Equal to the 0 and del of VQ and the del of VD. This is nothing but the different parameter that are generally used by comparing with the phasor diagram of the steady state, their concerned parameter to define the phasor diagram of that transient state analysis under the of the synchronous motor. Okay, so this is nothing but the phasor diagram under the transient state, which is nothing but the where XD should be XD should and the XQ is should be equal, XD is equal to the XQ and the XD dash is equal to the XQ dash. Means what? The steady state or direct axis in the steady state ED is equal to 0 and the EQ is equal to EQ, but the same is not true in the transient state. ED is equal to 0 हो जाएगा और E is equal to EQ हो जाएगा steady state में, but in case of the transient state is not a condition is there. Okay, so this is nothing but the EQ and the EQ dash. अब दोनों का डिफरेंस कितना आ जाएगा? Del of EQ is nothing but the XD minus XQ dash into the ID. Okay, so direct axis is there. This is nothing but the quadrature axis. That is the ID current is there. That is nothing but the IQ current is there. Okay, and this is nothing but the induced voltage across that. X is the dielectric axis. This is nothing but the quadrature axis. Okay, and that is del is nothing but the load angle or the power angle. Whereas E dash is equal to EI dash under the condition of the transient state, and the difference between the axis and the quadrature axis is nothing but the 90 degree. Okay, and this is the ED का value कितना है? That is the value of ED dash is nothing but a what? That is I into the PX minus PX dash. Okay, so this is nothing but the 90 degree angle between the dielectric axis and the quadrature axis of the transient. So under the transient state phasor diagram, the XD should be equal to the XQ, and the XD dash should be equal to the XQ dash under the transient state. But in case of the transient state, ED is not equal to the 0. Okay, and the E should be is equal to the EQ dash. This is the phasor diagram under the transient state. Okay, so in next lecture we have to discuss the sub-transient state analysis and its phasor diagram. Thank you so much.